In this video we're going to prove Fermat's little theorem. It's called that to distinguish it from Fermat's last theorem, so the thing about a to the n plus b to the n equals c to the n. But here's the statement. So Fermat's little theorem says that if you take a prime number p, and if you take an integer x which is not divisible by p, then x to the power p minus 1 is congruent to 1 mod p. Right, their difference is divisible by p. So the way we're going to prove this is by applying the corollary from our last lecture, which I've copied at the bottom there, to a particular group. So in fact to the group ZP cross. So you'll remember that ZP cross under multiplication was a group, and the set ZP cross consisted of the equivalence classes class of 1 mod p, class of 2 mod p, and so on up to the class of p minus 1 mod p. So all the equivalence classes in ZP except for the equivalence class of 0, which as you'll remember consists of all the multiples of p. Okay, well what we can say about this integer x we've got is, since x is not divisible by p, then the equivalence class of x, and I'm going to drop the subscripts p here in this proof, this equivalence class of x is not the equivalence class of 0, so it's actually in our group ZP cross, the multiplicative group mod p. So let's apply our corollary at the bottom of the screen there to this element of this group. So what we get out of that is, if we take this element of the group and we raise it to the power the size of the group, and the size of the group here is p minus 1, then what we get is the identity element of the group. And then our group ZP under multiplication, the identity element is the class of 1. Okay, these what we have on the left there is the equivalence class of x raised to the power p minus 1. So well, what happens when I multiply, when I take x to the class of x to the power p minus 1? So what I have to do is multiply the class of x by itself p minus 1 times. But if you do it twice, class of x times class of x, by definition of multiplication in this group, that's the class of x squared. So similarly, if I take the class of x to the power 3, that will be the class of x to the power 3, and so on. So what we'll get here is the class of x to the p minus 1 being equal to the class of 1. Now these two integers, 1 and x to the p minus 1, have the same equivalence class. If they have the same equivalence class, that means they're related under the equivalence relation we're talking about, which is congruence modulo p. So if they're related by congruence modulo p, what that means is that x to the p minus 1 is congruent to 1 mod p. Okay, so x to the p minus 1 and 1 are therefore related under our equivalence relation. So x to the p minus 1 is congruent to 1 mod p, and that has finished our proof of the theorem. So let's just take a moment and think about what this tells us. So for example, you might take p is equal to 17, you might take x to be equal to 7, that's certainly a number which is not divisible by 17, and then this would tell us, Fermat's little theorem would tell us, and we're going to write FLT for short, it would tell us that 7 to the power 16, some enormously large number, well, whatever it is, it's congruent to 1 mod 17. Okay, let's look at the kind of application, the kind of result that we can get at by applying Fermat's little theorem. And one of the useful things that you can use Fermat's little theorem for is for computing large powers modulo a prime. So let's consider this problem of looking at 7 to the power 1000 modulo 17. So you know it's going to be congruent to 1 of 1, or, well, I mean even better, 0 or 1 or 2 up to 16 modulo 17, but the question is which? Which of those numbers is it congruent to modulo 17? So as we just pointed out, Fermat's little theorem tells us that 7 to the power 16 is congruent to 1 mod 17. So we can use that to help us. We're going to use that together with the observation that 1000, if you divide it by 16, you get remainder 8. So 1000 is 62 times 16 plus 8. Okay, so there is our observation. So what can we get out of this? Well, I mean, what we're interested in really is we're interested in the equivalence class of 7 to the power 1000 under congruence modulo 17. So as we've just observed, this is the same as the class of 7 to the power 1000. And as usual, I'm going to drop those subscript 17s. And working inside the group Z17 under multiplication, so Z17 cross. Okay, so what I can do here is I can rewrite this as 7 to the power 62 times 16 plus 8. And we can use this trick of using the exponent laws, which we've done quite a few times now. So what we can do is we can just say this is the class of 7 to the power 16 all to the power 62 times the class of 7 to the power 8. So we're using the exponent laws in groups as we've done a whole bunch of times already. And as usual, we observe that the 7 to the power 16 is congruent to 1. So what you've really got here is the class of 1 to the power 62 times the class of 7 to the 8. But of course 1 is the identity element in our group Z17 cross. So 1 to the power 62 is just 1 again, or class of 1 rather. So what we have here is just 7 to the 8. Okay, so we've reduced this problem a little bit. Instead of having to calculate the class of 7 to the power 1000, we just have to calculate the class of 7 to the power 8, which is the class of 7 to the power 8. So you might think this is not such a great improvement, because I mean 7 to the power 8 is still a pretty enormous number, but we can actually make our lives a lot easier here just by doing working out 7 to the power 8 one step at a time. So what I mean by that is, well, let's work out class of 7 squared. So that's the class of 7 times the class of 7. That's the class of 7 times 7. So that's the class of 49. Okay, we're working mod 17, so that's the class of 34 plus 15. Okay, 34 is 2 times 17, so this is congruent to 34 plus 15 is just congruent to 15 again. So we have here the class of 15. Okay, now the useful thing about this is if I wanted to know 7 to the power 4, well, I can get that as the class of 7 squared times the class of 7 squared. So this is the class of 15 times the class of 15. But actually, an even better observation to make at this point is to say, well, actually, you know, I don't want to have to work out 15 times 15. That number is too big for me. So what I'd like to observe instead is 15 is congruent to minus 2 mod 17. If you take the difference, you get a multiple of 17. And it's much easier for me, instead of working out the class of 7 squared times the class of 7 squared, so the class of 15 times the class of 15, it's much easier for me to work out the class of minus 2 times the class of minus 2. Okay, so let's write down all the steps here. What are we doing? We're observing that this is the class of 7 squared times the class of 7 squared by the exponent laws. We're saying we know the class of 7 squared and it's 15, but we also know that it happens to be equal to minus 2. Okay, that's the class of minus 2 times minus 2, that's the class of 4. Okay, nice and easy. So the class of 7 to the 8 is now the class of 7 to the 4 times the class of 7 to the 4. That's the class of 4 times the class of 4 which is the class of 16, we're done. We now know that 7 to the power 8 is congruent to 16 mod 17, and so 7 to the power 1000 is congruent to 16 mod 17. Okay, so this trick where we which we use to evaluate 7 to the power 8 mod 17 is called exponentiation by repeated squaring. Okay, before I stop talking about computing powers modulo p, you might think that this is not necessarily that useful in real life, but actually it's something which turns out to be extremely useful indeed. So if you want to know a bit more, search for RSA crypto system or RSA encryption. So this is a method which is used very often for things like security on the internet, and it heavily involves computing powers modulo large numbers, and so this trick actually turns out to be much more useful than you might expect.